Welcome to this explainer. Today, we are decoding a highly counterintuitive physical phenomenon in aviation called adverse yaw. We're going to be exploring its history, the underlying physics, and honestly, some of the most ingenious engineering solutions we've come up with to beat it. I'm super thrilled to guide you through this, because the invisible forces of aerodynamics, they are absolutely fascinating once you know exactly what to look for.
Okay, so let's dive right into this paradox. Imagine you're driving down the highway, you turn your steering wheel to the left, but the hood of your car suddenly swings out to the right. Sounds crazy, right? Like a complete glitch in the physics matrix. But this is a very real challenge that has plagued pilots literally since the absolute dawn of human flight. So today, our main focus is to figure out exactly what adverse yaw is, what causes it, and how aviation pioneers and modern engineers have countered it to keep us flying straight.
Here is our flight plan for today. We'll start with the paradox of turning, move into what adverse yaw actually is, break down the aerodynamics behind it, and then look at the pilot's manual solution with rudders. After that, we'll check out the engineering solutions built right into the wings, and finish up with the cutting-edge future of Proverse yaw. All right, kicking things off is Section 1, the paradox of turning and the struggles of early flight. You know, the Wright brothers actually discovered this problem the hard way. Back in 1901, when they were testing their early gliders, they used this technique called wing warping to initiate a roll. And well, they found out that warping the wing absolutely created the lift they expected for the roll. But dynamically, the upward moving wing was unexpectedly dragged backwards. It caused the glider to yaw in the complete reverse direction of the intended turn. And if this violent yaw happened, the extra speed on the lower wing generated even more lift and totally reversed their roll. There was just no way they could make controlled turns until they finally added a movable rudder system.
Which brings us nicely to Section 2. What is adverse yaw? Let's get a solid definition of this phenomenon. Think about it like this. When you command a roll to the right, your right aileron goes up and your left aileron goes down. You obviously want to turn right, but the airplane initially yaws adversely out to the left. It's essentially a secondary effect of how lift and drag are distributed across the wings during that specific rolling motion.
So, by definition, adverse yaw is the natural and, frankly, super annoying tendency for an aircraft to yaw in the opposite direction of a roll, and it's caused by the difference in lift and drag of each wing. Now, it's really important to note that this adverse yaw moment is mostly present while the aircraft is actively rolling relative to the surrounding air. Thankfully, once you establish a steady bank angle and that roll rate stabilizes, this left-right lift imbalance kind of just dwindles away, and the adverse yaw largely disappears.
Moving right along to Section 3, the aerodynamics behind it. Let's talk lift and drag. Let's break down exactly what happens to the wing shape. When you lower an aileron, say on the left wing because you want to roll right, you are physically changing the shape of that wing. Just like deploying a flap, lowering the aileron increases the wing's camber, or its downward curvature, and that creates a higher angle of attack. Now, a higher angle of attack means more lift for sure, but it also creates more profile drag. Conversely, the aileron that's deflected upward on the right wing, that decreases the camber, producing less lift and less drag. But you know, it's not just profile drag doing the dirty work here. A deeper dive into the physics reveals that the real culprit is induced drag. Because that downward aileron is producing way more lift to physically raise the wing, it proportionally creates more induced drag. This induced drag effectively acts like a giant invisible parachute, pulling that upward moving wing backward. So your left wing is generating all this great lift to roll you to the right, but the massive drag penalty yanks the left wing back, throwing the nose of the plane out to the left. And this isn't just a constant, static force. It changes based on exactly how you're flying. You are going to notice adverse yaw the most prominently at slow flying speeds and high angles of attack. Why? Well, because at slower speeds, the aerodynamic pressure on your control surfaces is much lower. That means you have to use way larger aileron deflections just to maneuver the aircraft, which obviously magnifies that drag difference. You also see this massively on aircraft with really long wingspans. Think high-efficiency sailplanes and gliders. Their wingtips are just so far out that the drag creates a massive lever arm, pulling the whole aircraft off course.
Let's move to Section 4, the pilot solution, and how we use the rudder. To fully grasp the fix here, we have to keep the three axes of rotation in mind. Ailerons, they control your roll on the longitudinal axis. The elevator controls your pitch on the lateral axis. But to actually fix our adverse yaw problem, we need to focus on the vertical axis, the directional stability.
and that is controlled by the rudder. So here's the crucial technique. To perform a coordinated turn, a pilot must step on the rudder pedal directly into the direction of the intended turn. If you want to roll right, you step on the right rudder. Now, here is a super fascinating aerodynamic fact for you. The rudder doesn't just balance out the drag by creating more drag on the other side. Actually, no. The rudder acts like a vertical wing. It physically creates sideways lift to yaw the nose directly into the relative wind, actively countering the downward aileron's drag moment. You are quite literally manually overriding the physics glitch. All right, Section 5, Engineering Solutions in Wings. Let's see how we can fix this right in the design phase.
Over the decades, engineers realized pilots had enough to worry about, so they developed some incredible mechanical innovations to essentially trick the physics and reduce pilot workload. Now, modern electronic fly-by-wire systems, they can automatically mix aileron and rudder inputs, but mechanical systems have always relied on really clever physical geometries. We're going to take a closer look at differential ailerons and freestyle ailerons. Though I should mention, aircraft also use things like roll spoilers to basically destroy lift and increase drag on the descending wing, letting you turn without adverse yaw.
So first up, let's look at differential ailerons. This is just a brilliant workaround. It's actually been used since the 1930s on planes like the famous de Havilland Tiger Moth biplane. The mechanical linkage is configured so that the upward deflecting aileron actually travels a much greater distance than the downward one. By excessively deflecting that upward aileron, it intentionally increases profile and separation drag on the inside descending wing. That extra drag on the inside wing yanks the nose right into the turn, effectively canceling out the induced drag of the rising wing. Plus, because it limits downward aileron travel, it's a huge help in preventing wingtip stalls.
Next, we have Frise-type ailerons. So instead of changing the travel distance, this design fundamentally changes the hinge geometry itself. The aileron pivots on an offset hinge. When the aileron is raised on the descending wing, the forward leading edge of that aileron physically dips downward into the high-pressure airflow underneath the wing. Frise ailerons cleverly use this intentional form drag to counter the induced drag on the exact opposite wing. Think of it like sticking a metaphorical foot out the window on the side you want to turn toward. It literally pulls the turning wing backward to equalize the yaw.
Finally, we reach Section 6, the future of Proverse yaw. It's time to completely flip the script. So let's look at the very bleeding edge of aerospace innovation and how NASA is turning this entire problem right on its head. For decades and decades, traditional aircraft have used elliptical wing designs to minimize drag. But as we know, those natively produce adverse yaw. Well, expanding on some brilliant research by German engineer Ludwig Prandtl way back in 1933, a team at NASA Armstrong designed and validated a wing that uses a completely alternative bell-shaped span load. Rather than fighting physics with drag-inducing ailerons or big rudders, this sharply tapered wing uses twist to achieve a bell span load. And, incredibly, this actually produces induced thrust at the wingtips when you use the ailerons to roll.
The benefits of this are absolutely staggering. Because of that bell-shaped span load, the wing requires 12% less physical area, but allows for 22% more span. This translates into an immediate 12% reduction in overall drag. But the absolute crown jewel of this design, it natively produces Proverse yaw. When you input roll control, the forward thrust at the wingtip actually pulls the aircraft's nose directly into the direction of the turn. It rolls and yaws in the perfectly correct direction totally naturally. This exponentially increases the total aircraft efficiency by just completely cutting out the drag we historically had to rely on to steer.
And because the aircraft naturally yaws right into the direction of the turn, you completely eliminate the need for a vertical tail or heavy drag rudders. Imagine what the future holds for mid-sized commercial aircraft or even UAV drones. We're talking about sleek, highly efficient, bio-inspired flying wings soaring through the sky with absolutely no vertical stabilizers dragging them down. It perfectly mimics the flawless, tailless flight we see in birds. So, I leave you with this. The next time you're sitting in a window seat and you watch the plane bank into a turn, what are you going to see? Is it just a piece of metal? Or is it a true engineering marvel, perfectly balancing differential drag, incredibly complex geometries, and fighting a century-old battle with invisible aerodynamic forces? Thank you so much for joining me for this explainer. I really hope this leaves you looking up at the sky a little bit differently, and hungry to learn more about the incredible invisible physics keeping us all safely in the air.